Well, thanks for coming after lunch. Some of us rushed back and are very sad about our wet shoes, but whatever, it's fine. This is every time I come to California, it rains a lot. So you're welcome, I guess.
I'm more often.
Yeah, I know, exactly. Yeah, well, every time it's at the downpour.
Thank you.
So I'm actually very excited to be here at this amazing workshop that has so many different topics, none of which I'm an expert in so far from what I've heard, which is really good because I'm learning a lot. Like I know the words you guys say, but not necessarily all the details. And I'm wondering whether my talk will be the same to you or not. So I have two polling questions. Does anybody know what is a Helly number? A couple of hands. Does anybody know what's a Violator space? Okay, so I want to make sure, because if half of you raise your hand, then I'll change my tune here a little bit. But okay, so thank you for, and if you remain silent, it's your own fault, okay? For having to endure this. Okay, so I sort of gave a similar talk recently, so I have this one slide which, you know, whatever. Oh, click. There we go. Does this work? Yes. I have one slide that explains what nonlinear algebra is. I think we know, but just in case there are people wandering in from whatever, topology or something. I'm interested in solving systems of polynomial equations, so doing commutative algebra, but actually getting the solutions on a computer. Right? Unlike some commutative algebraists, which is fine, that's fair. So I'm staying on the applied side, and I'm looking for exact solutions. So there's this big field of numerical nonlinear algebra, numerical algebraic geometry, where you can, do these magic tricks of sweeping your varieties and getting witness sets. No, I want the exact solutions to my system, and I'll explain why in one example. And all examples that I consider in my work come from optimization, statistics, biology, or geometric modeling. These are all very popular topics in this journal that you probably know about, the SIAM Journal of Applied Algebraic Geometry, SIAGA. It's a cool journal where I don't have a paper yet, so I'm like really, but I mean, it's just such a broad field. It's really a top journal, I think, in the field. And the reason I want exact solutions is that we don't actually know how to get them efficiently. So the cornerstone of computational algebra is this really high complexity algorithm that we don't know how to bypass. And so I want to tell you a story about this. And I also want to sort of excuse myself for why I'm talking about randomness, because I actually work on algebraic statistics for the other half of my academic life. And so I'm very familiar with randomness. I study random models. I look at data and try to model it. And then I turn to algebra and say, where is your randomness and why are we not using more of it? So it is not true that algebraists are not using randomness. There's a history to this. I give you 3 snippets, none of which are what I'm going to talk about, but just to demonstrate that this is not a weird idea. So, oh my God, 1930, that's 100 years ago, right? So there's a paper by Little and Offord about counting the expected number. I cannot use a pointer, I'm sorry. Expected number of real roots of a random algebraic equation. So you have a polynomial, the coefficients are random, and you look at the number of roots, and then you look at the average, right, or expectation. That's a random variety, right? There are randomized polynomial time algorithms for testing polynomial identities. So that's a whole other line of work. And I'm putting like one paper. There's many more, but so sorry. And then there's this, more recently, this smoothed analysis of algorithms. And this, I learned this from my collaborators. It's think about having an algorithm that performs really badly in the worst case. And then you do a slight random perturbation of that worst case and see if you do better. So those worst cases are like really sharp points somewhere. You just have to push yourself off that point, and then your algorithm performs better. So it's kind of like a expected algorithm performance if you wiggle the points a little bit, okay? So the goal of the paper that we wrote, and I realize this is almost 10 years old, but there's a reason why I'm talking about it. It's the beginning of a long story, okay? So the goal that we started with was to come up with a framework for randomized algorithms for computing with polynomials so that I can solve the system, okay? And I'm interested in, I'm sure many of you know Jesus De Loera, and so if I quote him, I can't help it, but I have a musician's ear, so I copy people without wanting to. So I'm going to focus on average performance versus the pessimistic worst case, okay? But it's true. It's really true. I can't help it. That's how if I talk about you, I will sound like you. Like, that's just how it is. So it's I really am motivated by this because everything we do has the horrible worst case, and I still have examples I have to compute, and I put them in a computer, and I still somehow compute them. I mean, okay, like, what's going on? How do I understand this other average? And so I'm really going to steal ideas from two other fields, one being computational geometry and optimization. So I'm going to focus my talk on this today, efficient sampling techniques, so that we can get the algorithms to run better. And then, of course, I also work in algebraic statistics, where we are really good at sampling polynomials, okay? We just don't sell it to algebra very often. So in algebraic statistics, I can give you 1 million binomials from a very high-dimensional, toric ideal, and algebraists don't use that. So I'm here to implement that over here in algebra. Okay. So the question that I'm trying to solve is this one. It's a running example, so you can do it on a piece of paper, okay? It's a very small system here, but I'm going to call it large, because I'm going to pretend n equals 6 is actually n equals like 600 or 6,000 or 6 million, okay? So I have two types of equations in my system. One is just a quadratic, xi squared minus 1, and the other one is xi plus xj. Not every xi plus xj, only things that have opposite, parity, right? So I drew a picture of the system. You can probably see that the quadratic, polynomial or binomial corresponds to vertices in the graph. The values of the vertex can be, I had a big lunch with them, can be 1 or minus 1. I'm sorry, I'm dying over here. I had a big lunch, I had to walk 20 minutes uphill. Okay, fine, it's fine. I'm old, I have the privilege of this struggle. Yes, I'm very happy. So, and then I have this linear polynomial, which is basically corresponding to the edges in the graph. Okay, and I want to know if the system has a solution. Correspondingly, is the variety empty? And if you just think for 1 second, you'll see that this is a coloring ideal of a graph, right? Because the 1 and minus 1 can be the blue and red color on the vertices, and this equation demands that the vertices that share an edge have opposite colors, right? This is a 2-coloring ideal of a graph. I stole a slide by David from MIT. It was from this paper with Jesus De Loera, because he's demonstrating graph coloring has many applications, and it's not just 2 coloring, it's k coloring for any k. You can come up with a system, but I can't digest it in a talk, so I just do the 2 coloring, okay? So does the system have a solution? How do I check? Well, how do you check? You just run Macaulay 2. How many of you have done this? Thank you. More than half the room, but not the whole room, okay? So Macaulay 2 is a system that used to be very difficult to install on your computer, but now it's easy, but you don't even have to do it. There is a web interface, which I love dearly. So you can go online and, load it, and then just type an ideal and say, is there a solution to the system? And you do that by saying, give me generators of the Gröbner basis, okay? So gensgb is just a command, and I sort of put the code here to show you that, yes, I still, as a pedestrian, type things down and push enter. So if you're a grad student, do it, okay? It's worth the trouble, because then you'll code it up better afterwards. Okay, so I get a Gröbner basis, which consists of 1, 2, 3, 4, 5, 6 polynomials. So this is actually a solution, because the Gröbner basis isn't 1. So this polynomial tells me, I don't think you can see, but it's x6 squared minus 1. So if I pick the color for x6 to be 1 or minus 1, these other edges are all the neighbors of 6. And then I just tell it how to color the rest of the neighbors, and I'm done, right? I've given a value to every xi, so I have solved the system. And so this is the general algorithm for checking whether a system has a solution. Just compute a Gröbner basis of the given ideal. I don't care what term order you want to use, so whatever was the default in Macaulay 2, Gravlex. And if 1 is in the Gröbner basis, that's equivalent to taking your system, computing the row echelon form, and getting 1 equals 0, which is inconsistent, right? And so 1 being in the basis is exactly the characterization of having no solutions. Okay. How does Macaulay 2 compute the Gröbner basis? Well, it takes like no time, right? But it's running in the background this algorithm called Buchberger's algorithm. I have a slide about this later that maybe I'll get to. But the point is, Bruno Buchberger came up with the algorithm and the idea of Gröbner basis in his thesis in the 60s. And he basically proved that you can't beat his algorithm. It's like the basic thing you have to compute, and then people have come along and computed that the runtime of this thing is doubly exponential in the number of, in the size of the input, the number of input polynomials. And you can't get away from it either because there are examples where the output is doubly exponential in size. So in fact, this is horrific. And then, oh, whatever, like the simplex, just press enter and it works. It does until you have like more than like, I don't know, 6 or 7 variables. That's pathetic. So I teach my undergraduate students computational algebra, and I say, here, just do this. This is the algorithm. This is the state of the art. And they can't do the simplest system from an application because it's got more than 10 variables. It's just too complicated. So that's the main bottleneck. And if you ask Buchberger, how can I get away from this? His answer is you can't. Haha, you're stuck. You simply can't do any better. So let me give you a different system just to motivate how I'm going to come up with a different way to check whether the system is feasible or not. I added an edge, the red edge. This thing has wheels, and I just moved it. Okay. Okay. Well, I'm awake. Sorry, I know I'm on YouTube. Nobody's watching, right? So I added an edge. So I added the equation x1 plus x3. Is this graph too colorable? No. Why? I put the 3 cycle. Okay, ask the computer, just to make sure, Gröbner basis is 1. So this system is equivalent to saying 1 equals 0. We can see that. But if I had a 6,000 vertex graph and I added this little triangle and you try to compute the Gröbner basis, this algorithm won't finish. And I still know it's not colorable because of this little subgraph, which is an obstruction to coloring, right? So this is just the first natural thing to do is find the obstruction to coloring if you believe it's not colorable. Don't try to color the whole graph by trying to find the solution, every possible coloring solution, and then determine it doesn't exist, because that's what this is. It tries to find every possible solution. It says, I can't find any, right? So I want to search these obstructions to coloring. And so here's my different algorithm. Oops. My different algorithm is search for a subsystem that determines the same variety, so an infeasibility certificate. So look at all this is ridiculous, but here I go. Look at all the subgraphs of this graph and see if you can find one that you can't color. That's not an algorithm that you want to run, but in principle, right? So then, what if you knew that there is a size of the subsystem that you knew was going to be the certificate of not colorability or infeasibility, right? So I can detect that size by making the matrix of coefficients of the system, pretending this is linear algebra, although it is not. The difference being every column of this matrix doesn't correspond to x1 up through xn. It corresponds to x1 squared, x2 squared, and then x1 and xn. So all the monomials I had in my system are supports of the columns of the matrix, and then this is just a coefficient matrix of the nonlinear system. I can compute the rank of this matrix. If everything else is boring, just go compute this. I don't know, it's a graph matrix, okay? And so we tried this on a few examples and conjectured that the size of the infeasibility certificate equals the rank of this matrix. For my example here, it won't be 3. It will actually be, I want to say 9, because I'm going to give colors to all the vertices and then show that this thing will screw it up. Okay, so I guess I want to solve for all x's. So there's a minimal infeasibility certificate, but there is one that's guaranteed to exist of that size. So what's the meaning of this number? And if I knew it's the rank, all I have to do is not search all subgraphs of the graph, but only subgraphs of that size. I'm not doing so great with this algorithm, right? But I'm trying to improve it, right, from the down. And so here is, the secret is that that number is a Helly number of sorts, okay? So for those of you who know this will come very naturally. Let me just explain what the Helly number is and how this comes up here. So a Helly-type theorem for varieties is what I'm after. So I'm first going to state what original Helly theorem was. So any theorem that sounds like this. You are given a family of objects F and some property P, and there's a Helly number delta, then every subset of size delta having property P implies the whole subset has property P. Sorry, this should be F. There should be an F and a G because F should be subset of the other F, but I don't know why it's the same F. This is ridiculous, yeah? Because just same F everywhere. I don't mean that. I mean, I have a family of objects. This is a maybe different font. And then if every subset of size delta has the property, then the whole set has the property. The original Helly theorem was about convex sets and having a non-empty intersection. So you have a convex set in Rn, and you're wondering whether these convex sets have a non-empty intersection. They do exactly if every subset of those sets of size n plus 1 has an intersection. If I have 3 sets, this is silly. But if I have 3 million sets, this is cheaper to check. Okay? So I just want to take this idea, steal it, and translate it to my polynomials here. Okay? So in searching how to make this theft feasible, we found a paper by Frankel and adopted this idea. There exists a Helly number for varieties, and it's as follows. A set of polynomials has the D Helly property if for every non-empty subset you can find a certificate of size D where the varieties are the same. So there is always a certificate of the same size that captures your solutions. Okay? I know there are many letters floating around, but okay. And then we can prove, and this is sort of obvious a posteriori when you've imported everything, that a polynomial system of rank D has the D Helly property, so the rank of the matrix I had in the previous slide. So there exists a Helly number for solving systems of polynomial equations. Okay? Are you with me? Okay. So how do I use this? Well, now I know what this D should be. Now I really just have to find certificate subsystems. Feasibility or infeasibility, doesn't matter, because it captures the same variety, right? How do I find it? Search all subsets of size D. Steal something else from people who are way smarter than searching all subsets of size D. And here is what we're stealing next, okay? This is stealing. It's like a form of flattery. It's borrowing an idea, importing. I used the wrong word. Excuse my English, it's a second language. I used the wrong word. But I mean, it's actually motivating because they do better than we do. So I'm going to just write down what is an LP-type problem. And if this sounds like I'm switching topics, if you're a student, I am. And then I'll tie it back together in a couple of slides, okay? So bear with me here, okay? So what is an abstract LP-type problem? Okay. I have a finite set of constraints and then a real value for every subset. If it's too abstract, just think of the classical example, smallest enclosing ball problem. So H, the constraints are the points in RD. Okay, so I select a finite set of blue points, G, and I compute the radius of the smallest ball that encloses them. This red, I'm going to pretend it's a circle. Okay, so this is an LP-type problem, anything that you can formulate in this way. Okay, and so what is the radius? Well, I can either specify the radius for you, or I can tell you how many points define a circle, 3, right? Okay, in R2. This is going to be in RD, so I'm going to need D plus 1 points for the ball. But if you tell me these 3 blue points are enough to make that circle, then we're going to call those 3 points a basis. So I can either specify the radius or just the 3 points that make the circle. Okay? So solving this problem is equivalent to finding a basis that explains what will make the circle. Okay? And so the key here is that solving an abstract LP-type problem is equivalent to finding a basis. Whoops. Finding a basis of H. So now let me tell you what is my H. Okay? And what is my basis? Are you with me? This is also a Jesus question. Right? Okay. So here's the definition of a violator space. This is the most beautiful thing I have learned in the last 10 years, I think, from outside of my field. In my opinion. So it's something that generalizes LP-type problems, and it's a framework to which the fastest algorithm out there actually applies most generally. So a violator space is just a pair. There's H, which is a set of constraints, and V, which is like a mapping. And then I say a constraint H violates G if this value changes when I add H inside. So a point violates G if it lies outside of the smallest ball. Okay? Do I have a picture? I do. So if you look at your G being this set, right? There are two blue points that violate this set here. Okay, so it sits outside. The mapping, violator mapping, is any mapping you want to define. Okay, so this is very abstract. So it just has to satisfy two axioms. And if you think about this, this is just logic. I mean, okay, so you should not violate yourself. You're in the ball or you're out of the ball, right? And then if you have this inclusion property and you don't grow the violators, then you haven't grown the violators. But because everything is so abstract, you have to have the axioms mathematically make sense, yeah? And then we define a basis, a minimal B, that captures all of the violations. Okay? So in the same way that these two blue points would be a basis of this set, I'm going to say these two blue points are basis of the violator space, where the violation is telling me if I'm outside of the circle or not outside of the circle. And so the thing that I really liked about this is this, there's this algorithm called Clarkson's algorithm, which is a clever way to sample until a basis is found. And so Clarkson did this algorithm for LP-type problems. That's the 1995 paper, okay? And then Gartner, Matuszek, Rustin, Skovron proved that this can be used more generally in violator spaces, and also proved that it cannot be used in anything more general than a violator space, okay? So what is Clarkson's algorithm? Okay, so what it does, it samples from the set until a basis is found. I know I need 3 blue points to make a circle. So how about I pick these 3 blue points? Have I made a circle? No. I mean, I have made a circle, but it doesn't enclose everything. So throw the points back, try again. Have I done it now? Try again. Have I done it now? Try again. Eventually, I've done it. If I keep going back and throwing my points back, I'm doing the dumb algorithm of sampling all the subsets. Clarkson's ingenious idea was, before you throw these points back, tell me how bad is the violation. So this set has only one violating point outside versus this set. So when I throw the points back in the bag, I bias towards the points that were reaching small violating sets. I don't want to necessarily keep them. I want to sample with replacement because I don't actually know if I'm going to need these 3. In fact, I won't need this one. But these 3 did better than these 3 and then these 3, right? So you just keep sampling and keep telling your algorithm how to bias the sampler next time. This is just Bayesian statistics, y'all, okay? Except it's discrete. So what do you need to make the algorithm work? Oops, I want to show you the theorem, but what you need is 3 ingredients. You need the definition of a violator mapping. I mean, obviously. You need to know what delta is so that you can sample and resample 3 points and not sometimes 3, sometimes 5. Because if you have that wrong, then you don't know that you're going to get an exact solution, right? And you need a primitive. A primitive is just an algorithm that says, are you outside or are you not outside? So does the check of determining whether something belongs in your set or not. So the theorem, okay. I'm not crazy. I'm petrified of spilling water on my computer. Done that before. Okay, so I am crazy. I'm petrified of spilling water on my computer. So the theorem is that this algorithm works and it's expected linear time. So I'm spoiling the beans. That's on the next slide, okay? But I want to, instead of telling you the Clarkson theorem, I want to tell you the way we use it, okay? So for us, we made a mapping. It's called, we made a violator space called vsolve, because I'm solving the system. And I'm going to declare that to be the set of all polynomials such that when I look at the solutions that polynomial has, it changes from my set, right? So I add a constraint and I change the solution set. So it's needed for the variety set theoretically, right? Theorem, this is a violator space. Go check the axioms. Go check that this makes sure. What's the basis? The basis is exactly up to radicals, these ideals are the same. Okay, they capture the same solution sets. we already proved that Helly number exists, and we can show that this is the combinatorial dimension of this violator space. So the problem is when you make this definition, it implies what should be the rank, and it implies what should be the basis. So if you make a definition too convenient, the rank is wrong. So you have to make a definition just so that you understand what delta will be. So for us, it was the Helly number, okay? And so now the theorem is, and the primitive query is, you do have to do a Gröbner basis computation, but it will be small. It will be on the set of 3 blue polynomials and not the entire system. The first time I talked about this idea was you don't remember many talks probably that you give over the years, but I remember this because I explained this in a FOCM conference in Montevideo, and people in the audience were like, you're replacing Gröbner by Gröbner over and over and over and over again. Like, how is it? I mean, right? Like, what am I doing? But that's Clarkson's idea. And the theorem that he has that we are able to translate is that actually will bring down the computation time. And so we take their algorithm and we say it's a sampling algorithm. I'm like putting it in the same words they had because I don't want to do the notation. It outputs a basis of the system that has the same solution set. So a certificate of feasibility or infeasibility of size delta in expected number of this many calls to the small Gröbner basis. And then you have to do a little bit of algorithm complexity analysis to make sure that this is smaller than the W exponential run of the big thing, okay? And so to demonstrate, how do you demonstrate that the theorem works? You code it up in Macaulay 2, and you run it on an example that you know you're going to beat, right? So I am not claiming that this theorem gives you an algorithm that is always faster. That is false, right? People have worked on Gröbner basis implementations for many, many, many years, and some of them are very, very, very fast. But in a bad cases, their algorithm doesn't finish, and we do it in 8 seconds because of this expected. So on average, we do much better. So the worst cases go away. Okay, and so of course, what is this example is the Meyer-Mayer ideal. Why? Because if you have not heard about this, go look this up, okay? I know, right? Thank you for, of course, what else do I
It's the worst one, right?
It's the worst thing out there. It's the reason why we know Gröbner bases have double exponential size, pretty much, okay? And then I make it worse because Macaulay is smart, right? Macaulay 2 knows, the software, or I guess the people who wrote it, know how bad this is. So they do a bunch of tricks to help us along and actually do a computation. So I make it worse. So I add, a product of the first 10 generators plus the constant 1, okay? So that's going to be equal to not 0. So it will be infeasible. And then I add a generic homogeneous cubic in this ring, and it contains 5,456 terms. I'm just going to break Buchberger because Buchberger's algorithm does these S polynomials and divisions, and it carries with itself this debt of trailing terms. So I'm making sure that it just can't finish, okay? Am I cheating? Well, yeah, to demonstrate the worst cases, okay? Sorry. But it's incredible that, this is 8 seconds. That's not really 8 seconds. That's 8 seconds of my Macaulay 2 code at the top level. If I did this properly in the engine and as pre-processing, it would probably be much faster, okay? Questions? Or did I lose everybody? There's no third option. Either I lost everybody or there are questions. Yes.
So would it be the same if you added polynomials and it was still feasible?
Yes. Okay. Yes, what my problem was that I wanted to make sure that I can by hand tell what the solution is, because I never trust my code. It's just code, but I never know exactly what I did. So I wanted to make sure that this is 1 equals 0, and then I know I'm done. Yeah.
So I'm just making sure I'm the expected runtime is big O of delta M plus delta
yeah.
of delta. So that's the expected average runtime. That's the average runtime?
That's the average runtime.
Okay, so
it could still be bad.
So it could still be double exponential.
It could.
If the random choices were bad.
Correct.
Okay,
So then you just do it again.
Right. Yeah.
Right, yeah.
Right. No. Okay. But
Exactly.
okay. So
Yeah.
this is why you're not saying this is always going to be better. But if you take a bad example and you do it 50 times and you don't let it go too long,
Exactly.
one of those times.
Exactly. Yeah. Exactly. I mean, it's just statistics of different sorts. Yeah. Exactly.
Sure.
Yeah. Thank you.
Word expected, you somehow need to like bold it and put it a little
Will do.
hard around
Will
it.
do. Will do. Thank you. Will do.
It took me a moment to.
Yeah. I think I get lost also in the words because there's so many things I'm saying, and I'm just making sure you understood. But then that is the big point. Yeah. Thank you. All right. So 305. Okay. So I wanted. Okay. So I wanted to say. So now what? And the now what was actually the story of me struggling to decide what to tell you in the talk because there's so many ways this can be taken now. And here is what we're doing next with this violator spaces. And then I'm going to explain what are all the different directions in which we can go. Okay? And I'll pick one to tell you a little bit. And so in ongoing work with Shahrzad Jamshidi, we cook up this thing called the Spark randomizer. It's a new way to compute a Gröbner basis based on the algorithm I just showed you. Because why not? I mean, why don't you? And what are the ingredients? Well, there's an input system. There's machine learning number one, machine learning number two, some universe. This is Clarkson, but not really. This is Bayesian Clarkson. Because we have predictions, blah, blah. Some primitive check and output is a Gröbner basis. Okay. I squint because there's a lot of open questions here and a lot of things we don't know. What I do know is that I'm going to get expected linear runtime in the size of the input. If, and I know the output will be correct, okay? And I have to do machine learning for prediction, okay? I don't know how to improve accuracy for prediction because I'm not a machine learner. But that's why I have collaborators. We need to figure out how to sample efficiently from this universe. So all of these are question marks because if these if these things are working well, then the framework works with a theorem, like a violator space theorem. But there are many moving pieces. And so I chose to tell you, kind of about this part here because just to demonstrate what we did to make a violator space, because the rest feels like a completely different talk. But I wanted to demonstrate that they're not solved problems completely. We're still working on it. I don't think we need this. So what's the state of the art of Buchberger's algorithm? And why did I make the Mayer-Meyer examples fail? I kind of said it in words, but here it is in writing. It's an old algorithm, and there are many, many specializations, variants, improvements. And the state of the art is it's actually faster than Buchberger thought it was going to be. It works on a few variables. And there are many improvements, but they all leverage the same idea, which is this computation is generalizing Gaussian elimination. It's trying to tell whether 1 equals 0 or not, and it's trying to give you this row echelon form type thingy in a nonlinear fashion. And so all the improvements construct these crazy, complicated techniques. I don't even understand all of them, but they are trying to perform Buchberger's key step, which is this reduction of Buchberger's S polynomials, okay? So everything is based on this. I love S polynomials, but I don't want to compute a single one, okay? That's the goal, because if you rely on this, you cannot do better. And so I want to depart from this idea of having to compute S polynomials, okay? I know he proved you have to compute them. I just really don't want to, because as a statistician, you don't really have to, right? Okay? And I want to focus on this average performance. So what is this violator? It is not the same violator that I told you. And one of the reasons I wanted to discuss this is that perhaps you're working on a problem where you have a large set and you need a small certificate. And perhaps you can just define the corresponding violator space for your problem and then get an algorithm to give you a basis and then go from there, okay? I know examples of this in numerical algebraic geometry where you pre-process a huge system of 1 million polynomials. This is a perfect example of how you can use it. So pick any monomial ordering. I have a leading term, okay? And I'm going to define a new violator space. V induced by that monomial order. It's just going to be the set of H's that tells me that this is not a Gröbner basis, right? So it has leading terms that are new, that are not generated by S. This is the obvious definition, because the definition of a Gröbner basis is when LT equals everything, right? You check that this satisfies violator space axioms. If you try any minor modification of this, it doesn't satisfy the axioms, okay? So it's just a bit of homework, okay? What is the largest basis? Well, it's the largest basis is when you can't find anybody who violates it. So this is exactly a minimal Gröbner basis, right? And now I know that this is a Gröbner violator space. And I know that the basis of that space is the minimal Gröbner basis. All I need is its size. But this is fine. I'm just going to predict it with machine learning. And we do well. And I'm just going to quantify the uncertainty of my prediction and tell you the probability with which I'm wrong in my output. And this is fine. Right? Because maybe, okay. I mean, I don't know. You could either, I'm just looking at you because you're smiling. I'm like, either I'm
waiting to your
question. Yeah, there's a million, there's a million things I don't know how to answer, but this is fine.
Yeah, we all trust it with prime numbers. This is fine.
It's insane. It's okay. So, but blah blah blah. Clarkson for Gröbner. I can do this, and I have the primitive query. Okay. What's the primitive query? Well, I need to decide whether an element satisfies the, you compute the leading term. This is a monomial. Check. This is easy. So I can do this. All I need to do is figure out the combinatorial dimension, which are the two pieces here. Oh, did I say it here? No, I did. Sorry, I forgot a slide maybe. So I have two machine learning algorithms predicting the size of a Gröbner basis and the max degree of a Gröbner basis element. Okay, and I'm not crazy for trying to predict these using machine learning. There's a precedent for this in computational algebra community. So the brief story is the following. Dylan Pfeiffer was a student of Michael Stillman. He graduated in 2020. And his thesis was using machine learning to predict something about the Buchberger algorithm. And the something he predicted turned out to be a new rule for running Buchberger. And then they implemented that in Macaulay to speed up a bunch of computations. So it's not like crazy. Although what he wanted to predict was much better defined than what I'm trying to predict, but that's okay. Basically, they had a bound, there are some existing upper bounds, and there's some core belief that you can actually, if you phrase the problem well, you can use machine learning techniques for this. And what we did was also relied on, this was an undergraduate student, Jelena, working with me, Mojsilovic, she's now at Purdue. In the PhD program, and so we sort of, Laura, what's her name?
Lily.
Lily. I was like, is that Lori? I said, I'm so sorry. You don't, if you're listening. Lily Silverstein, she's at Pomona now, right? She's like nearby. So in her thesis, she also had some machine learning predict something for another algorithm for Hilbert bases. So this is doable if you phrase your algorithm properly. We're not sure that we're phrasing algorithms properly because this is what the data looks like, and you're trying to classify, the yellow points have high Gröbner degree and the other points have low Gröbner degree, and this is just a mess, okay? This is not the best plot, but it's just one to show that this looks horrible, and it's unlike what machine learning traditionally does, right? Machine learning is good with images. You squint, you see it, right? And then you train a computer to do this on a bunch of data. So this is slightly different. Okay, but and we didn't do so well in the first run, but then we kept trying to improve it. And so I don't want to talk about this, but I wanted to say, what is this H? So this is the set of all possible polynomials in my ideal of degree at most m. You don't want that set. But that set contains the minimal Gröbner basis because I know the degree bound. So just, if you're not sure about your prediction, just double it, whatever. You will contain a Gröbner basis or something like this, right? I'm never going to compute this set. I'm going to sample this set into existence, which is why we're departing from Clarkson. So Clarkson has the universe of blue points. And then he samples 3 points at a time. I am blind to my blue universe, but I'm constructing samples because this is what we do. We just sample from there. Theoretically, we know what the structure is. So we start spitting out polynomials and then do a Bayesian correction to make sure this thing is built into existence, okay? So it's bad, but it's also doable because it's just statistics. I don't know if I sold it or broke it, yes.
So for arbitrary polynomials of degree up to m, like that's basically what you're looking at, right? Then is there some well-known Markov chain that you can on this so you can sample? I mean, I know that there's like the Markov models for binomial stuff, but like if I'm just looking at arbitrary polynomials, is there a sampling algorithm that?
There is not a sampling algorithm. So I went to the Field Institute to run an apprenticeship project last month, and a group of us worked on how do you sample? Question mark, that's it. Like, so there are different ways you can sample different algebraic objects. There's a package in Macaulay 2 which is just random. It's called random ideals. It's just random. It's not like a true sampler. We have good models for sampling monomial ideals. We have good models for sampling binomial ideals. And beyond that, we kind of don't know. I have a half of a model for sampling toric ideals because of the combinatorics and the matrix A, and I know how to do this really well. But I don't know anything else. I do know we could use, I guess, what is this, Brunsification. So maybe we can just talk about ideals, 3 generated ideals forever, but then they have to be long, right? So I don't know how to machine learn on things that have arbitrary length. So I don't know how to sample for arbitrary objects, and maybe that's the work of the next 10 years. Or maybe, you know.
But I think I saw maybe on an earlier slide, but if you do this, yeah, like there.
This one that I tried to hide?
Yeah, that one. So, but if you do have, say, toric things, then you can make this work better.
If I have binomial things, I can make it work better. If I have toric things, we're not done. So Sarah is now running the algorithms to predict. So I don't know if we can do better, but we should be able to. But like binomial is certainly better because also binomial ideals make sense from the point of view of Gröbner basis because as polynomials remain binomial, everything's binomial. So you're learning things that are, it's always a vector. In a computer, it doesn't have this long tail or whatever. Does that make sense? Okay. And so I have a whole bunch of problems that I can ask, but they are like spelled out in our paper with Sarah. This is Sarah, and I don't know why. I just decided I have to put a picture of her because she hasn't gone to conferences the last couple of years for having 2 kids. So she deserves to be well known, but I'm maybe here on her behalf, okay? And so I'm done with my talk, but here's an advertisement just in case you were not aware of this amazing conference happening in July. I failed to put the dates, July 7 to 11, so right after 4th of July, the week, in Madison. And it's the SIAM conference on applied algebraic geometry. And I swear the schedule will be online any minute now. I'm the program chair, so I know the schedule already. There's a lot of amazing talks. There are 2 mini tutorials on the first day about TDA for neuroscience and metric algebraic geometry and lots of good talks coming up. So I hope you will join us. There's some funding available for students in particular. So if you're not sure and if you're like, I missed the deadline, but I want to go, you could just email me. So I'll end here.